So the live streaming has begun. Should we begin in another 2 or 3 minutes? Hello, am I audible?
Yes.
Okay. So shall we begin in about 2 minutes or so?
Yes.
Okay. Thank you. Shall we start?
Yes.
Okay. So hello everyone. I welcome you to the 7th lecture on quantum chemistry on quantum computers by Professor Kenji Sugisaki. Today he'll be talking about computational complexity. So he would cover topics such as computational complexity classes, including ones in classical computing like P, NP, etc., and those in quantum computing like BPP, BQP, QMA, etc. Professor Sugisaki.
Thank you very much. And welcome to the 7th lecture of the lecture series of the quantum chemistry on quantum computers. And today I'm going to talk about somewhat different topics from the other lectures. And today I'm going to talk about the computational complexity. And this is, as I said, somewhat different from the lecture on the quantum computers, but it's very important to understand what kind of problem can be solved on quantum computers efficiently or not. So let us start by thinking about the motivations. Let us think about these 5 problems. For example, it includes sum of 2 integers of n digits, product of 2 integers of n digits, and find the greatest common divisors of 2 integers of n digits, and factorization of n digit integers, and solve n integer in ascending order. Of course, you can easily imagine that some of the problems are easy, but some others are not. Let's say the summation is very easy, but the factorization is very difficult, usually, especially for the large n in these integers. So let us think about how to quantify the difficulty of the problem. So, and also how to classify the problem in terms of the complexity. So let's think about the illustration that think about the investigation on the scaling of the number of elementary steps against the problem size n. So it means that how much the computation cost increases if the problem size n become twice or become larger. So in order to discuss this problem, first we have to specify what is the elementary steps in computers. So I would like to introduce the Turing machine. Turing machine is a mathematical model of computation. It was proposed by Alan Turing. It consists of a control unit with a finite state. So it means a CPU with the finite size, and a tape unit with a head that moves from one tape cell to a neighboring one in each unit of time. So it means that the Turing machine is basically consists of the finite size of CPU and infinite size of memory. And the Turing machine works something like this. First, raise the symbol X of the particular cell, and then write the symbol Y according to the state of the CPU X and the symbol X. And then move or unmove the tape to the left or right and change the state of the CPU from X to X dash, and then return to step 1 or half. An important thing is that any computation can be realized. Any computation that is capable by performing on computers can be also realized by using this Turing machine. So in this case, these steps correspond to the computation steps. Also, I'd like to introduce the big O notations. Say in this lecture series, I always use the big O notation, but here I would like to define the meaning of the big O notation. This big O notation calculates the function according to the growth rate. So the big O notation is defined as like this: f equal g if there exists a constant c such that fn is smaller than c times gn for every sufficient large n. So roughly speaking, this big O notation is describe the bottleneck steps for very large problem size, when the problem size becomes very large. So, for example, if the Fn equal to n plus 3, this can be rewritten as f equal order n. If the Fn equal n squared plus 4n, in this case, the bottleneck becomes this term, so f equal order n squared. If the Fn equal 2 to the nth power plus n, in this case, this part is a bottleneck, so f equal order 2 to the nth power. And also, I would like to introduce the big O tilde notation. In this big O tilde notation, we ignore logarithmic factors. So roughly speaking, the order Hn, order tilde, Hn equal order Hn log n. An example of the big O tilde notation is the factorial transformation. The factorial transformation of length n can be solved in order n log n. So in this case, we can ignore this log n factor by using this big O tilde notation. So order n log n equals order tilde n. And why this kind of notation is used? This is because the behavior against the problem size is very different from among each other. I mean, if this is the graph just plotted by as the n versus fn, and if the fn equal just log n, the fn is very small even for n equal 100. But if the n equal fn equal n squared, because in this case, if n equal 100, the fn equal 10,000. And if the fn equal 2 to the nth power, the fn is very small, even only for the small n size. But if n becomes large, the fn strongly increases. So, roughly speaking, the practically solvable problem should be in the polynomial scale. So, I mean, if the computational scale is something like order 2 to the nth power, it can be solved for small n, but it becomes impractical if n becomes very large, because fn becomes easily reach to astronomical figure, even for small n. So exponential scaling is usually very hard to solve, except for small problems like n. But important thing is that from the practical point of view, problem in exponential scaling is not always harder than just in polynomial scaling. So this is an example of the two functions, which one is 1.0001 to the nth power. So this function is exponentially scaling versus n to the 10th power. This is a polynomial scaling. But in this case, let us think about n equal million cases. The first one is just 22,000, about 22,000. But this is exponential scaling, but still, if the n equal a million, but this function is still just 22,000. But this is a polynomial scaling, but if n equals 10 to the 6th power, this value becomes 10 to the 60th power. So in this case, the polynomial scaling is much more larger than the exponential scaling for practical point of view. But usually, we think that the practically solvable problem should be in the polynomial scale. So based on this thing, I would like to define the complexity class. The complexity class is a set of functions that can be computed within given resource bound. So there are two types of complexity. One is the time complexity, which corresponds to the computation time or number of steps of the problems. Another complexity is the space complexity. This is roughly speaking the memory space, how many memory we need to solve. In order to discuss the computation complexity, we will pay attention to the Boolean function. So have only one bit of output. So the output is either yes or no, or 1 or 0, or true or false. And the first complexity class is class P. This P means the polynomial time. So the problem in class P can be solved by a deterministic Turing machine. This is just a Turing machine I described before. So the class P problem can be solved by a Turing machine using polynomial amount of computational time, or just a polynomial time. So the scaling of the problem in complexity class P should be order n to the sixth power, where c is some constant rather than 0. And the complexity class P includes, for example, summation and multiplications and primary case, and finding the Eulerian path. I will explain the Eulerian path in the next slide. But the important thing is, as I said before, the polynomial class P is the problem that the computational cost scale just polynomial against the problem psi, but it doesn't mean that it is always practical for computers. So let's think about the good example is this AKS algorithm. The computational cost of the AKS algorithm is something like this. So roughly speaking, it's polynomial, but the n to the 11th power, about 11th power. So in this case, the primary case is polynomial, but using AKS algorithm, but it is very difficult to apply for large integers. So let us introduce this Eulerian path. The Eulerian path is very famous, but usually the Eulerian path is explained by using this Konigsberg 7-bridge problem. The Konigsberg is a birthplace of the very famous philosopher Immanuel Kant, and also mathematician David Hilbert. And this is a map of the Konigsberg. The name of the town is now in Kaliningrad in Russia. And currently there are 1, 2, 3 bridges and 4 bridges, but previously there are 7 bridges like this. And this 7-bridge problem is something like this. It is possible to devise a walk through the city that will cross each of these bridges once and only once. So let's think about, let's say, starting from this place and go every bridge is something like this, and only once and to devise all the bridges. Why this problem is very famous is that this Leonhard Euler proved this problem is impossible. I mean that impossible to devise all the bridges once and only once by using this graph. So in this case, we define the place as A, B, C, and D, and translate the bridges as nodes. So in order to devise a bridge, work through the city that cross each of these bridges once and only once, is translated to the problem to cross the node only once. So roughly speaking, the problem is becomes something like the writing this graph in one stroke. For example, starting from this place and write all the nodes in one stroke. In order to cross each node once and only once, there are two requirements. The one is the graph is connected. And another is the number of vertices with all number of nodes should be either 0 or 2. So in this case, the number of vertices count the number of vertices with all number of nodes. This vertex has 3 nodes, connected nodes, and this B has 5 nodes. This C has 3 nodes, and D has also 3 nodes. So in this case, the number of vertices with all number of nodes equals 4. So it means because each node only once is impossible for this graph. In this problem, even the number of vertices or number of nodes increases. In this case, the n can be think about the n equals the number of vertices. The computation cost is always polynomial, just counting the number of nodes for each vertex. So this problem can be solved in polynomial time. And we will introduce another complexity classes, the class exponential. This class exponential problem can be solved by a deterministic Turing machine using exponential amount of computational time or exponential time. So the computational cost gain is something like 2 to the order Pn's power, where Pn is a polynomial function of n. And the problem included in exponential class is, for example, finding the Hamiltonian cycle. I will explain this Hamiltonian cycle in later. It is obvious that P is included in exponential. This means the problem that can be solved in polynomial time is also solvable using exponential time. But the problem that needs exponential amount of time is not solvable in polynomial time. But the sum of the problem is also solvable in polynomial time. I mean, the problem in class P is also solvable, of course, solvable in polynomial time. We will introduce another very important complexity class NP. In the class NP, we introduce 3 conditions in addition to the polynomial time. The first condition is it allows non-deterministic choices. So, for example, you can use dices or choose based on your intuition. Another condition is use the computation cost of the worst case. And also, we ignore if the answer is no. The class NP problem is solvable under these three conditions in polynomial time. This kind of problem can be easily understandable by, for example, when I think about the escape the maze. When I think about you are here from you're here from this way, and you can select left, right, or left. So you can use dice or coin tossing to go right or left. And this means that if the this means that if you have a paper that includes the answer of the maze, you can find this. Go here and turn left and left and right and left and right and left and right and so on. Ignore if the answer is no, means that if the maze is not escapable, in this case, we don't think about this maze. So we always think about in the case of maze, there are at least one answer. And for the problem in class NP, we can verify whether the instance is correct or not using the combination machine in polynomial time. So in this case, if you have this kind of paper, you can verify this is correct or not by using polynomial time. Just following this. And the problem in class NP includes such an existence of Hamiltonian cycle and satisfiable problem. You can easily understand this NP problem is included in expansion, class expansion. So if you don't have this kind of paper, you can go, for example, right, and if the right corridor is the cul-de-sac, you can back to the original place and go left and so on. So the number of such space is just within the exponential, basically. So we can introduce the Hamiltonian cycle. Hamiltonian cycle is first introduced by using an Icosian game. Icosian game is something like this: find a cycle along the edges of a dodecahedron, such that every vertex is visited a single time, and the ending point is the same as the starting point. So in this case, this Icosian game is very easy. You can easily solve by yourself. And this is one of the example of the Hamiltonian cycle. In this case, this cycle visits all the vertices once and only once, and the starting point and the ending point is the same. So why this problem is very famous? Because once finding the Hamiltonian cycle is quite difficult, becomes quite difficult for the graphics with large number of vertices or edges. And also, you can easily understand that once the Hamiltonian cycle is given, verification is very easy. So let's think about this kind of graph. And as you can imagine that finding the Hamiltonian cycle using this of this graph is very difficult. And the number inside the circle corresponds to the number of edges the vertex have. I also like to introduce the satisfiability problem. SAT. The satisfiability problem, or SAT, is a propositional logic formula, also called Boolean function expression. It's built from the variable operator and or and not and parentheses. Example is something like this. X1 or X2 and X1 and not X3 and X2 or X3. And this instance is true. So, for example, in this case, we are thinking about the situation X1 equal 1 and X2 equal 1 and X3 equal 0. So X1 or X2 is satisfied because both X1 and X2 are 1 state. And X1 and not X3 is also satisfied because X1 is 1 and X3 is 0. So not X3 means that this one means that 1 state. And X2 or X3 is also satisfied because X2 is 1. We define the NSAT problem. The NSAT problem means that each class is this was expression in the parentheses has at most n regulars. So regulars means that some let's say the variables. And why this Hamiltonian cycle SAT problem is very famous is that in the context of completeness and hardness. So let me define first the complete problem. And NP-complete problem means that the problem Q is in NP-complete. If Q belongs to the class NP, and any problem in class NP can be translated to the particular instance of the problem Q in polynomial time. So roughly speaking, NP-complete problem is the most difficult problem in the class NP. And NP-complete examples of the NP-complete problem existence of Hamiltonian cycle and three SAT problem. Also, I would like to introduce the NP-hard problem. NP-hard is a problem Q is in NP-hard if Q is at least as hard as the hardest problems in NP. So this instance can be, this completistic classes can be easily understood by using a diagram, Venn diagram. First, let's think about the problem in P. NP problem is outside of the, includes the problem in P. But here we assume that the P not equal NP. And there are NP hard problem. This intersection area, the connect between the NP and NP hard correspond to the NP complete problem. So the problem in this area is the problem, the hardest problem within the NP problem. In order to discuss the complexity classes of the quantum computer, first we have to introduce the class BPP. But before discussing the class BPP, I would like to introduce the probabilistic Turing machine. The Turing machine I discussed in the beginning of this talk is the deterministic Turing machine. But here, I would like to discuss the probabilistic Turing machine. This probabilistic Turing machine, or PKM, is the computation. It proceeds something like this. The non-deterministic Turing machine or probabilistic Turing machine is this PKM is a non-deterministic Turing machine with two transition functions, delta 0 and delta 1. And to execute the computation using PKM, we choose in each step we probably 1/2 to apply the transition delta 0 and 1/2 probability to apply delta 1. So roughly speaking, this PKM always performs the coin tossing to perform the computation. And the class BPP is defined like this. The decision problem can be solved by a probabilistic Turing machine using a polynomial amount of computation time or polynomial time with an error probability bound away from 1/3 for all instances. The BPP means that the bounded error probability polynomial time. So this bounded error comes from this error probability bounded away from 1/3. And of course, the probability comes from the PKM. And polynomial time comes from this polynomial amount of computation time. As you can easily imagine that because the PKM using a coin tossing or probabilistic selection, so this computational class is a strong connectivity, strongly related to the computation complexity in quantum computer. So let us define the complexity class for quantum computers. First, I would like to introduce the class BPP, BQP. BQP is a bounded error quantum polynomial time. So BQP is a decision problem, so it can be solved by a quantum computer using a polynomial amount of computation time or polynomial time with an error probability bounded away from 1/3 for all instances. So the difference between BQP and BPP is just here. BPP uses a probabilistic Turing machine, but BQP uses the quantum computer, quantum machine. So we can say that the class BQP is a quantum analog of BPP. And also, I would like to introduce another important computational classes for quantum computers. I mean, the class QMA, quantum memory alpha. The problem in class QMA, for the problem in class QMA, we can verify whether the instance is correct or not using quantum computer in polynomial time. So this class QMA is the quantum analog of NP. So next, I would like to think about what kind of problem is included in QMA. So I would like to introduce the K-log Hamiltonian. K-log Hamiltonian is very simple about the Hamiltonian H which is a linear combination Hj, where each Hj acts only on k or less qubits. So let's think about the qubit Hamiltonian, where the Hj is expressed by a Pauli string. In this case, the k log Hamiltonian means that every Pauli string has at most k Pauli x or Pauli y or Pauli z. I mean the non-Pauli, non-identity operators. So, and also in the computational class, we always think about the Boolean function that are yes or no. The answer is yes or no. So in this K-local Hamiltonian cases, yes means that this Hamiltonian has an eigenvalue less than A. A is some value. And no case that all the eigenvalue of the H are larger than B, well, B minus A is bounded as larger than 1 divided by polynomial n. And in this K-local Hamiltonian, we can easily understand this if the K equals 1. So I mean the one local Hamiltonian is in polynomial, okay, class P, because let us think about the K-local Hamiltonian with the pi operators. In this case, the eigenfunction of the fourth system is just a direct product of the eigenfunction of the one qubit. So in order to solve the one local Hamiltonian, in order to obtain the eigenfunction of the one local Hamiltonian, you can perform only you have to do is perform the eigenvalue calculate, solve the eigenvalue problem for every one qubit system. So in this case, even the number of qubits increases, the computational cost increases just a polynomial or linearly. So the one local Hamiltonian is P. But think about the 5 local Hamiltonian. In 1999, the 5 local, it was proved that the 5 local Hamiltonian is QMA complete. How about the K within between 1 to 5? In 2003, 3 local Hamiltonian is QM complete was proved by Kemp and Wezer. And for 2 local Hamiltonian is also in QMA complete. It was proved in 2006. So you can easily understand the imagine that the quantum chemistry problem, such as solving the fluxy I, is QMA complete because the Hamiltonian translated to the qubit Hamiltonian is, of course, not in one local Hamiltonian, but K local Hamiltonian with K rather than 1. So let us summarize the relationship of the computational classes. First, P is included in BPP, and also BPP is included in BQP. So problem in class P can be solved in polynomial time using quantum computer. Because BQP is a problem that can be solved by using a quantum computer in bounded error in polynomial time. And also, P is included in NP, and NP is included in QMA. So P is here, NP is here, and QMA is here. And also, BQP is included in QMA. BQP is here, and QMA here. So this is very natural. I mean, the problem that can be solved in polynomial time on quantum computer can be verifiable by using in a polynomial time using quantum computer. Another important thing is NP is not included in BQP. So NP is here, and BQP is here. So this diagram includes very important thing. I mean, the NP complete problem is somewhere around here. Because if the NP complete problem is in BQP, I mean, this area, in this area, all the problem in NP can be translated to the NP complete problem in polynomial time. So it means that all the NP problem should be included in BQP. But because the NP is not included in BQP, the NP hard problem is somewhere around here. And also BQP complete problem is somewhere around here. So let us think about the more detail of the computational complexity of electronic structure problems. First, this paper was reported in 2014. The Hartree-Fock method for translation invariant systems is NP complete. In this case, there are some restrictions for the translation invariant system. But very recently, the electronic structure problem in fixed basis is Turing complete was proposed. And let's think about the complexity class of density functional theory. This paper was reported in 2009. In this paper, they proved that finding a universal function for density functional theory is QMA complete. This is maybe this is very natural because they when about conservation is based on the one-to-one correspondence between the density and the wave function. So solving the exact wave function is QMA complete. So it's naturally that finding a universal function is QMA complete. Another important complexity class of this function theory is the N-representability problem. The N-rep condition N-representability problem is also QMA complete. But the time-dependent density function theory for the excited state calculation. In this paper, they discuss the computational complexity of the TDDFT method, and they proved that the computation computing the time-dependent constant potential is BQP. So it means that computation of the time-dependent constant potential can be performed by using a quantum computer in polynomial time. We can use the computational classes for variation quantum algorithm. In this paper, they prove that the training variation quantum algorithm is NP hard. So roughly speaking, the train variation quantum algorithm is very difficult even for quantum computers. Honestly speaking, I'm not the professional of this area. So in the final slide, I would like to introduce you the very papers. And general review for the computational complexity theory can be found in this book chapter. And the computational complexity for quantum chemical calculations is summarized in this paper, TCG paper. Also, this paper is also available in archive. You can find many BQP complete problems in this archive paper. Also, you can find many QMA complete problems in this paper. If you are more interested in the computational complexity, please refer this book, the computational complexity book. The lecture some was short, but this is the last of today's talk. And thank you very much for your kind attention.
Thank you very much, Professor Sugisaki, for the wonderful talk. Are there any questions? I have one question.
Yes.
It's not directly relevant to BQP itself, but is it known if is the relationship between BQP and NP understood, or is it unclear whether it is contained in the other?
BQP and NP. Yes.
Yeah, I mean, the drawing here shows that there are parts of BQP that are outside NP, but is this known? Because yeah, sorry, that's
yeah. The basically the BQP is not in some of the BQP problem is outside of NP, and also some of the NP problem is outside of BQP. So basically so this means that some of the NP problems can be solved in polynomial time using a quantum computer. The problem in this area can be solved by using quantum computer in polynomial time. But some problems in NP cannot be solved in polynomial time, even by using quantum computer, because the problem can be solved in quantum computer in polynomial time is defined the class in BQP. So problem in this area cannot be solved on quantum computer in polynomial time. So you can easily imagine that this area includes some NP complete problem. So roughly speaking, the quantum computer is capable of some problem that is intractable for a classical computer. That problem is somewhere in this region, and P, but not in P problem. But even if for the quantum computer, some problem is also intractable.
Okay, thank you. Are there
Hello,
any other
I have
questions?
a question.
Yes.
Okay.
In the Hamiltonian cycle, you have shown you can go around the vortex. So how do you define a vortex? Means what does it mean? In the
Hamiltonian path.
yeah.
Hamiltonian cycle.
Yes, this one.
Yes. So could you come the question once again?
So for a problem, how do you define a vortex? If you have to go around around the vortex for a cycle. So how do you define a vortex for a definite problem?
Define the physics for some problems. So let's say that it's very your question is related to the graph theory. I mean there are some particular problem to the physics knows. So well, it's very hard to answer, but it depends on the problem. Only I can say it depends on the problem. So
Thank you. Are there any more questions? If not, then let's thank Professor Sugisaki for a very nice lecture today.
thank you very much.
Thank you very much.